Okay. Okay. Thank you, Rachel. And thank you. I want to thank to Phoebe Baker, Rachel Stokes, Alex Whitehead, and the University of Liverpool for organizing these webinars and for inviting me. And also, I would like to express my gratitude for the support given generously to me by distinguished academic colleagues, such as Leonor Bonin and Professor Redwan Shari at the University of Neuchâtel in Switzerland, Professor Carl Friston of University College London, Professor Dwight Reed of the University of California, Los Angeles, and Professor Michael Walker of the University of Murcia in Spain. It's been a pleasure to work with these people, and I have learned a lot. And so I wanted to start by thanking all of you, also the people that is interested in this webinar. As you can notice, I'm not a native speaker, and often my accent gets in the way. So I'm going to try to talk slower than I normally do. We Spanish speak very fast sometimes. That does not work in English. So I hope by talking slower, everything is more clear. I also warn you that I'm going to cover different grounds and offer different perspectives. So maybe you are not familiar with all what I want to bring here today, but don't worry. I mean, then there is the questions and I can clarify whatever you require from me. Okay, so let's get started. Lots of ground to cover. First, I would like to offer a definition of working memory. This is a definition that is included in a recent, let me see that I have this screen here. I need to remove. Okay, that's good. Okay, that's fine. So we can define working memory as an attention-based short-term storage system responsible for the manipulation and integration of past knowledge with present information for goal-directed behavior. And working memory is a key executive function and a principal predictor of general intelligence. It is important to think of working memory as something that is time-limited and also capacity-limited. And this is important because it helps us to distinguish working memory from other types of memory. For instance, sensory memory is a fleeting memory. It takes like few seconds, not more than 5. And you can store vast amounts of information, but it never gets into the working memory. So it's something that is fleeting and it disappears. And I tell you this because in the literature, this kind of memory has been conflated with working memory in chimpanzees. And this has created a lot of confusion. In the same way, we need to distinguish working memory from short-term memory. Short-term memory needs to store information for a short period of time, is capacity limited, but we do not engage with that information. So we do not manipulate, we do not operate with that information. Unless we engage with that information, it's not working memory. Okay, so these are things that we need to keep in mind because otherwise it's very confusing when you try to draw parallelisms between or across a species. Okay, okay, yeah. Okay, so the reason that we did the studies I'm going to talk you about was because a few years back, we realized that there was this image of chimpanzees as having an extraordinary working memory that was reported sometimes as rivaling or outperforming humans. And we three, Michael Walker, Dwight Reed, and myself, were convinced that this is not what the data show. And there had been some kind of misinformation, or this idea had originated in works that were not they had some methodological limitations or conceptual limitations. So we considered that it was very important to address this properly and to conduct a very thorough and critical review to really find out how is working memory in chimpanzees or great apes in comparison with that of humans. And the first challenge we faced to do that was that there were very few studies tapping onto working memory directly. So And this is something surprising, given the importance that some authors give to working memory in human evolution, like Coolidge, Wynne, and some other authors propose that this is key in our evolution and our cumulative culture and so on. So it was striking to find so many, just a handful of studies that directly try to measure working memory, and some of them have had serious limitations in terms of methodology and concept. So we didn't have much to revise, and so we decided that we could overcome that difficulty by turning our attention to studies that could be analyzed from the perspective of working memory computational demand. We would focus on three main subsystems that have been associated to working memory. One is a holding subsystem for working memory that is related to the capacity, how much things you can store. A strategic subsystem of working memory for enabling the establishment of goals and sub-goals for guidance of behavior that involves hierarchizing your behavior. And lastly, an attentional subsystem that would allow us to focus on the singular features of the surroundings and also filtering out distractors. What I mean by this is that we selected many studies with great apes and mainly chimpanzees that had investigated planning, or that in their problem solving they would require attentional control. And by revising those studies, we could draw conclusions about how was the size of their working memory. So it was a kind of indirect measure, but because we could gather lots of data and lots of studies, we think that we reliably measure the actual size of working memory. Okay, before I tell you what we saw in the revision of our results, I would like to distinguish between two types of memory that are important and that should be differentiated. Is pure versus effective working memory size or capacity. So the ability or capacity of working memory is measurable by tests and experiments to evaluate its size. We're talking of size, how much things we can store for a short period of time. And we are using the distinction that Nelson Cowan at the University of Missouri made to base our comparison. So he distinguished between one storage-specific working memory, designating its size as the pure capacity limit of working memory, and a process relating short-term working memory, designated by us as the effective working memory size. So pure working memory size relates to the architecture of working memory, and the effective working memory size to the implementation of that architecture. The measuring of the former, the pure memory size, requires eliminating any performance implementation, such as chunking or rehearsal, repetition, for instance, that can increase the number of units recallable from working memory. Cowan argues that the average size of pure working memory size is of 4 plus less 1 in humans, and with that he refers to the chunks of information that can be simultaneously held online, ready for manipulation in a focus of attention. He talks of this focus of attention when you can store up to 4 units of information or chunks of information. Okay, so when we investigated or analyzed a considerable number of studies that had tested cognitive capacities in great apes and in chimpanzees, we could establish which was the size of their pure working memory and their effective working memory. That's what I'm going to summarize here. The size of working memory in chimpanzees, what we found is that it's of size 2 plus less 1, well below Miller's famous 7 plus less 2 in humans. Comparable differences occur in experiments on chimpanzees relating to strategic or planning and attentional working memory subsystems, which refers to what we call the effective working memory size. Regardless of the domain, working memory performance by chimpanzees never exceeds that of a 4 or 5-year-old child. Much publicized claims of great chimpanzee ability are wide open to justifiable criticism. of the experimental designs and procedures on which the purported claims are based. There is abundant convergent evidence supporting a significant difference in the storage capacity, that is the size of human and chimpanzee working memory. On the other hand, the evidence supporting an extraordinary working memory storage capacity on the part of chimpanzees is scarce and often originates from the unorthodox adaptation of human memory tests. One other thing that we concluded in our thorough review, this extensive review of the literature, is that what I'm going to summarize now. There are two important takeaways from our 2022 review study. And these are not only the size of working memory of chimpanzee is of 2 plus less 1 chunks of information, which is below the 4 plus 7 plus less 2 of humans, but also, and this is very significant, PAN lacks the marked difference that is found in humans between a storage-specific pure working memory size, which is in human of size 4, and the executive or effective working memory size, which in human is of 7. This difference suggests a relationship between the evolution of human behavior and the evolution of aspects of cerebral neurobiology involved ontogenetically in the development of human working memory in immature individuals. Okay, so what we saw in this review, in this first review of 2022 that I conducted with my colleagues, Dwight Reed and Michael Walker, is that not only there were differences in the raw capacity of storing information, where we could call pure working memory, that in chimpanzees is of size 2 and in humans of size 4. But more importantly, in humans, the effective working memory is of size 7, but there is no increase in chimpanzees. So in chimpanzees, the pure working memory and effective working memory is the same. What does this mean? What this suggests is that chimpanzees do not engage with the contents of stored in order to boost performance. For instance, humans can use strategies to boost performance. So with this size of 4 chunks of information, they can deploy strategies like repetition or rearranging the information. For instance, if you keep some individual letters to recall, this person can form words with these letters and then can boost performance. This is something we didn't see in chimpanzees. So we did another study, another review of sorts, where mainly Dwight Reed, who is an accomplished mathematician, revised many studies of working memory size in human children and adolescents, and also with chimpanzees. And he plotted this data coming from many different studies. And this is what you see in this graph. I'm going to try to walk you through this graph. What we find is the pure working memory size, which is the size of working memory when you do not engage with the content. So when you do not try anything to improve your recall. Imagine if you ask you to recall something and at the same time, you need to repeat A, B, A, B, A, B. This is articulatory suppression. That will mean that you cannot engage with the information, and I will be measuring your pure working memory size. So pure working memory size is the raw power to store information without trying to improve your performance by using a strategy. And this is what you see here in the graph. Pure working memory size is like the raw power of working memory. And then we have the executive working memory size, which is all that you can store in short-term working memory by any device you can deploy. Okay? So in this graph, you have a line in black that represents the size, number of chunks of information that you can store as a function of age in months in humans. Okay? This is humans. And in the x-axis, you have the age in months. What you see basically is that from birth, there is first an acceleration of an accelerated increase of the storage capacity of working memory that almost reaches an asymptote. At the age of 36 months, we are close to 4 units of information, which is the maximum. And then there is a very small increase until 80 months when children have all the maximum storage capacity in their pure working memory. That would be that they have all the raw power they are going to get, all the processing power, without engaging with the information. And then happens something that we find extremely interesting, which is that until adulthood, that we reach a capacity to store information in working memory of 7, the magic Miller's number, there is a steady increase of working memory. So this increase is something we don't find in chimpanzees. Chimpanzees, if you see the blue line below, what you find is that they don't have this accelerated increase of the storage capacity working memory. Their increase is very linear and goes from 1 to 3 at about the age of 120 months. But then that does not increase further. So it stops there. And there is no effective working memory size. So it's like the main idea that we extracted from this graph and this result is that at some point in children, there is no more storage capacity in terms of space or raw power. The engine there is no more power there, but at that point, they start to learn how to apply strategies to make the most of this storage capacity. On the other hand, chimpanzees do not seem to engage with information in a way that would improve their performance. So the difference would be more related to executive control over the content of memory. Okay, this is something I'm going to summarize now also. Now, how the developmental growth of working memory size in Homo and Pan compares? What can we conclude from this second revision we published in 2024? The increase in working memory performance beyond the age of 8 years in humans cannot be attributed to storage capacity alone. Therefore, it is reasonable to assume that what changes is the executive control over its content. That is, the way these contents are engaged with an executive part of working memory. In other words, what seems to happen in late childhood and continues in adolescence is that children start to restore to devices, what we call mnemonic strategies that help them to recall more information from a limited space pool of 4 items or chunks. We believe that this is connected to changes in metacognition or meta-memory. Okay, what can we say? Another thing that we did in this study, and this is something that Dwight Reed and Michael Walker explore mainly, is how the storage capacity of working memory relates with growth of white and gray matter of the brain. And what we find is that the growth pattern for gray matter does not match the growth pattern of executive working memory size for humans. However, the white matter growth is similar to that of executive working memory size. And what we saw is that by around 18 months, when pure working memory size has reached its maximum value of 4, and brain weight has reached its maximum value, the gray matter volume is reducing, but white matter has not yet reached its maximum volume, which suggests that it is the increase in white matter that facilitates the increase in executive working memory size through aiding the development of mnemonic strategies, such as rehearsal, for instance, repeating the information, or chunking, each of which is known to increase the executive working memory size measure of working memory beyond its pure working memory size value. Okay, that's what I wanted to say about the working memory capacity of chimpanzees and humans. Then in the in the question round, I can elaborate on these things. But I would like to mention briefly another study that we finished. Well, I mean, Leonard Bonin and Redwan Shari mainly did this. I just helped a bit. And it's part of the thesis work of Leonard Bonin that tries to tap onto the working memory or the alleged working memory of cleaner fish, Labroides immediatus. And the reason for exploring working memory in this fish comes from the observation in the wild. And these fish do remarkable things. For instance, and then Leo, if you are there and you want to correct me, I'm going to just give some examples how these fish do extraordinary things or what appear to be extraordinary things. For instance, they have this kind of cleaner stations where fish come in the coral reef to get rid of ectoparasites. So these cleaner fish feed on ectoparasites from other fish, okay? But they prefer mucus and other things of the fish that they shouldn't be eating. So sometimes they can bite the client instead of eating the ectoparasite. So that would be like cheating. And I think to remember that these cleaner fish behave differently if they are being observed. So they cheat less when there are observers. So it's like when someone is observing, they give a better service to the client. And this is something that appears to be very interesting from a cognitive point of view. More importantly, there was one study like last decade in which they compared the performance of cleaner fish with capuchin monkeys, chimpanzees, and orangutans in a complex foraging task. And I'm going to tell you about this task so that you figure out what they did. This task consisted in offering them 2 plates to the fish with food. The food in one plate would disappear shortly, and in the other would stay very long. So the best foraging strategy for them was to learn that they needed to feed in the ephemeral food plate because then they would have time to go to the other plate. If they reverse the order, they could only get 1 piece of food, or they would just feed on 1 plate. So this is the type of task that has been used initially in scrap jays. Anthony Dickinson in Oxford did this experiment where the birds could vary food that was perishable in a short time, in a waiting interval that was short, or after a long interval. So if they went for the long interval, this food would have disappeared, it wouldn't be edible. So they needed to select first the plate of perishable food and then the plate that had permanent food. And this has been, again, used by Joseph Guy and Hemaur Das with, I think to remember, bonobos. I don't know which grade I think it was bonobos. And they offered them to choose between 2 choices of food. One was an ice cube, the other was grapes or bananas, I don't remember. And they had to choose one of the 2 options after different intervals. In the short interval, if they went for the food, the ice cube in the short interval, it was an ice cube of juice. It would have been melted yet, and then they could go for the other food. But if they went for the option ice cube after a long waiting interval, the juice wouldn't be there anymore because it would have melted. So these tasks are supposed to tap onto what has been called episodic-like memory. And they appear to involve very complex computational, or they require very complex computation. So seeing that these fish can outperform orangutan and chimpanzees in what is thought to tap onto episodic-like memory, one would expect that they have, I don't know if I would dare to say powerful working memory, but at least we would expect to find some complex memory. And so Leonard Bonin and Edward Shari at the University of Neuchâtel did one study to specifically tap onto working memory. And the study consisted on something similar, offering two options of food to place where the fish could feed. And the most simple experimental procedure would be like they explore one plate and then they offer two plates. The one they had explored and that they had was baited before, but they had eaten the food and now it's empty. So what is expected is in second choice, they go for the new plate because the other they have already emptied it. They have been fed with that plate. So they need to remember, this is a test that could be solved on the basis of familiarity. We need to have this sense of familiarity with the plate that was presented before in order to alternate and go to the new plate. So the best for eating strategy, or the only one efficient, is to change plate in the second choice, okay? And in this experiment, what they found were very weak positive results in preferring the new plate. That was the only one that remained baited, still had food. The most disconcerting thing is that when you give them many trials, this trend disappears. So the more trials, the more trained they are, the less they go for the non-visited plate. And so this is like a bit disconcerting. Apart from this experiment, in this thesis work, there are several more experiments that try to tap onto working memory. And the problem we had with these studies is that this simple two plates, choosing between two plates, was thought like a warm-up. We wanted to train them to do this, to then go to the actual test of working memory that would involve some kind of sequential learning. It would be more complex. But they failed in this first, like, training or warm-up phases. So we ended up concluding that with these 4 experiments, the results were so poor that we were unable to establish any kind of working memory in this species. And the reason I bring this example here, apart from being an excellent study, a very thorough, very well thought experiment conducted by Leonard Bonin and Redwan Shari, is because it shows something that is very relevant. If you see these fish solve their problems in their ecological environment, they appear to be extremely efficient, extremely intelligent. But then you ask them to do something seemingly simple in comparison, far more simple, in an artificial environment, and they do very poorly. So one wonders whether they needed any kind of executive conscious control to solve their kind of the problems they encounter in the wild. And that will go also for other species. So we need to be very careful, because sometimes we tend to make assumptions and we believe this involves working memory, but then it does not. So we need to make sure first that we get the definition right, because what I see often in the literature, and this is very dismaying, is that working memory is conflated with short-term memory. Working memory is conflated with sensory memory. Working memory is investigated without making sure that you control that they are not using long-term memory to solve the task. And so the results are extremely confusing. And you need to really clean up the results and make sure they adapted, the concepts were right and the protocol were right. They were good controls. Otherwise, it is impossible to draw any reliable conclusion. Okay, with that I finish this part. I'm going to introduce something that is kind of related to working memory, although a bit more different. And this is something that this is a couple of papers we published where we try to explain from a mechanistic point of view, from looking at the brain and how it works, why humans have this complex cultural and especially technological world, while other species like chimpanzees that are very versatile in their behavior and very inventive do not live in a complex technological world. So most of the explanation for this comes from social dynamics. They focus on dominance or who is the model for what, and social transmission. Many people focuses a lot in innovators or innovation, but very few people has focused on the working of the brain to provide an answer. And this is what we try to do. And I'm going to introduce ideas that maybe you haven't heard about, but that I think are important to understand evolution of the cognition in humans and other species. So what we wanted to know is which is the brain mechanism that allow and or prevent the accruing of technological complexity in any given species. And we attempted to identify what the minimum cognitive requirements are that can give rise to innovations and their horizontal and vertical transmission. We also wanted to differentiate the cognitive ingredients necessary for innovation from those necessary for the adoption of innovation. We have proposed the concept of zones-bounded surprisal that are the individual whose individual social gradual expansion would permit technological cumulative complexity in an animal species. So zones-bounded surprisal is a concept we have created that tries to explain why some species accumulate knowledge across generations and others do not. And to explain what this, or to understand what these zones are, I need to give you some background on the Bayesian brain and some new theories. So Bayesian brain theories is a contemporary cognitive explanation about how brains function regards our mind-brain as it projected forward in time. That is to say that it always is in the business of predicting what may be going to happen next, as if following probabilistic Bayesian rules. According to this explanation, the brain is not perceiving the world in the sense of building an image of reality in response to received sensory information. It is not a kind of mirror that represents inputs to it by representing or reflecting them to us for our appreciation or consideration. Instead, the explanation puts it the other way around, namely, that the brain builds the world outside before receiving any sensory information. That is, it anticipates the world. And then when it samples the environment, the sensory information gathered is used to check whether its predictions hold true. So metaphorically, we can think of the brain as making something akin to updating a map. You do not draw a map from scratch every time you want to have an update. You use your own map to superpose on the old one what it is that you now see, and any new future you now draw on it, like a new road. This way, you are spared from drawing everything anew, and so save yourself time and energy. What I'm going to tell you, on this idea of the zones-bounded surprisal, we draw from applying a type of Bayesian brain theory or framework, which is active inference under the free energy principle. And this is a framework that is based in statistical thermodynamics and was developed during the last 20 years by the psychiatrist, psychologist, and physicist, Professor Carl Friston of University College, together with many authors all around the world. This is a book where you can have a very good explanation of what active inference is. I highly recommend it, and you can download it for free. Now I'm going to introduce some last concepts that relate to this active inference framework, the Bayesian brain, that are necessary to understand our concept of zones-bounded surprisal. It's the concept of sensory attenuation, self-information, that we might consider like opposite concepts. Our brain is attenuating sensory information on a regular basis. For instance, our eyes move rapidly and suddenly in what technically are called eye saccades. And when that happens, the incoming stream of visual information ceases, sparing us the dizzy experience of perceiving a visual world that is jumping and jittering. Interestingly, we never experience a black visual screen when the incoming visual information stops being processed further, that is attenuated. And that is because the brain uses fallback images, that is stored offline information that fills these temporary gaps. This shows that the brain generates our experience, the world, and what we experience is not the passive reflection of the exterior penetrating through our senses. And to further understand this, I'm going to share with you an anecdote that a colleague of mine told me that I think is very informative to understand how our brain works. This is an anecdote of one guy and some other friends were experimenting with this substance that is called psilocybin. Commonly they refer to as magic mushrooms. So are these hallucinogenic substances, psychedelics, if you will. And the anecdote goes like this. He told me they were having this substance and they took it like an experiment. So they all experimented with things like, in this case, they were all wearing masks. This group of people were having this psilocybin while wearing masks. So the mask covered their faces, okay? And at first they could see each other masked. But at some point when this substance was in full effect, so to speak, was kind of, would have the maximum effect, this colleague of mine reported that he was unable to see the faces in others, and the others were unable to see the mask in him. So they were looking at each other, and they were unable to see the masks. So they were all wearing masks, but when they look at each other, they saw the faces behind the mask. They were completely unable to register the mask. What does this mean? How is this interesting for what I'm talking about, the Bayesian brain? The brain knew the guys, knew the voices, recognized the voices, recognized the clothes. So the brain knew what was hidden behind the mask, and it directly offered to them. So they were unable to see the mask, even though they were wearing the mask, because the brain credited the expectation. The participant's brain was so absolutely confident in its prior expectations, knowing which is the face of the person, that attenuated all sensory incoming contradictory input, that of the mask. So the sensory information of the mask were not being processed by the brain. So this is very telling. What this tells is that what any creature can consciously register is a matter of the confidence afforded to previous expectations as compared to the sensory incoming information. Crediting previous expectations may lead to sensory attenuation, whereas creating contradictory incoming sensory information results in self-information. This example shows, to some extent, that we see what we expect to see, not necessarily what is out there. And this is something that in neuroscience they call dynamic precision weighting. So there is a downstream of information that bears predictions, and there is a bottom-up stream of sensory information. And this information cross, and at this kind of crossing, so to speak, you need to decide whether you trust better the predictions or the bottom-up sensory information that contradicts the predictions. If you credit the predictions, then you can not even register the sensory information that is contradictory. In this case, it would be the mask. On the other hand, if you believe this sensory bottom-up information that is often referred as prediction error, then that would force you to put into question your predictions. Your predictions might be wrong, and then you can revise them. And this is very important for our concept of sense of bounded surprise. Let's see. Okay, so let's go to our concept. Zones of under-surprisal. This is a new concept that we introduced in 2022 in the paper To Copy and Not to Copy, and refer to the levels of mismatch between prior beliefs or expectations and sensory information that an animal species can tolerate. First and foremost, the focus of the zone of bounded surprisal concept is on the observers and their ability to make sense of an observed innovation. Encoding and subsequent copying of an innovation depends on the degree of disparity, surprisal in the technical jargon of information theory, between predictable behaviors, namely those typical of the species, those you expect in others, and the perceived incoming information about novel behaviors. If the zone of bounded surprisal is wide or porous, it means that a member of a species can give credit to the information received through its senses, which challenges its prior expectations. In short, this member of a species can register, encode, and potentially reproduce innovative or novel surprising behaviors, observing conspecific animals of the species, which deviate markedly from the customary prototypical behavior of the species. We might refer to this species as being highly impressionable, to use the word of Carl Friston in a discussion we held a few years back. These species that have a wide zone of bounded surprisal are prone to self-information. If the zone of bounded surprisal is narrow, it compromises a species' ability to change prior expectations, prior beliefs, in order to accommodate new evidence regarding innovative practices observed in others. Such a species will be more likely to attenuate sensory information that doesn't match previous expectations. It is a species that it is not prone to self-information. So in that regard, we think that in humans, when they observe a conspecific, innovate, invent something, they can show this through imitation. They can imitate it right away. And that is in virtue of having a wide zone of bounded surprisal. Whereas in chimpanzees, they tend to emulate rather than imitate truly through imitation, because they have a narrower zone of bounded surprisal. So they have more problems to bound surprisal, to tolerate surprisal. And they would do like in the example of the mask, they would, when they observe something that they do not expect, they might not even register it deeper. Now, I'm going to try to relate this concept of zone of bounded surprisal to working memory. A few years ago, we published a little book about the evolution of working memory, my colleague Michael Walker and I. And in that, we use this phrase, blending reality among different potential spheres, to refer to this capacity that humans have to juggle with many different objects or perspectives simultaneously. Which is a capacity akin to counterfactual, or entertaining multiple potential outcomes. This indicates tolerance of novelty and assimilation instead of rejection of cognitive surprises, and thereby reflect a wide zone of bounded surprisal that forces the human facility for registering, encoding, experiencing novel behavior, in contrast to the narrower zone of bounded surprisal of other animals, which include even the versatile chimpanzee. Without doubt, our greater working memory capacity enables innumerable cerebral permutations and combinations of information to be handled simultaneously and instantaneously translated into spontaneous responses of behaviors that we may never have performed hitherto, but that do not provoke a cognitive surprise because we have great tolerance to surprisal. From unanticipated observation or experiences, human individuals can glean information that enables them to update their expectations without necessarily having to conform to customary behaviors performed by themselves or others. And that's basically all I wanted to tell you. So I know it's a lot of stuff, so please formulate any questions you want.
Thank you very much, Professor, for a really great talk. We already have some questions in the chat, so I'll just start reading those out. The first one is from Walter, and he asks, is there any information about working memory in senescent brains, humans older than 60 and aging chimps? And I will just mention that we have a couple of your co-authors on the call as well, Professor Walker and Dr. Bonin, I think. Yeah, so if they would like to answer as well, that's fine. Yeah, carry on.
I think this one would be better addressed to Michael Walker if he wants to answer it, because he's the true expert in this kind of stuff on the brain. So maybe he's willing and able. Michael, can you answer the question? I don't know if he has. Michael, do you have the mic on?
Hello.
Now.
Hi. Did you hear?
Well, I think so. No.
It's not working, right? The sound.
I can't hear very well. Can everyone else hear?
Me neither. I can answer. I mean, Michael, you have a problem with the microphone. Something is wrong with your microphone. I can try to answer the question myself.
Okay.
Okay, so again, you said, Rachel, can you repeat the question, please?
Yeah, I'll read it again. Is there any information about working memory in senescent brains, so humans older than 60 and aging chimps?
I mean, there is a lot of information in senescent brains, and what the main message is that it's reduced capacity. I mean, I don't know how dramatic the change is, but in senescent brain, you lose kind of executive function capacities. So I'm not expert. I haven't reviewed the literature, but I know that there is some kind of decline. I don't know how bad it is, but we do know that. I do not know. Well, I know in chimpanzees something, because we did an experiment with this simple reversal that I did myself with Joseph Kai. We found something very exciting. This simple reversal is a measure of executive control, if you will. It's a simple reversal. It's quite of simple, going against rigidity of thought, if you will, or rigidity. So what we found is that adults were more flexible than both very young individuals and very old individuals. So old individuals were more resistant to change, more inflexible. So you would say that they have less executive control. So I guess I cannot relate that directly to working memory, but we do have data that indicate that senescent chimpanzees, if you will, or very old chimpanzees, orangutan, etc., are less flexible. Also less innovative, because we did some experiment also with orangutans. They had to invent a new use for a tool. And I remember that very old orangutans were never discovering this new use, while younger individuals did discover it, most of them. So I have some evidence that there are effects in their cognition. I don't know if I answered the question. Michael would do a better job of this.
If his audio is working, then we could try, but that was a really good answer. That's really interesting. The next question is, can learning be correlated with working memory size and repetitive actions, or are repetitive actions more important for learning?
That's a very interesting question. We know in humans that, and that's very interesting, we know that working memory, if you test working memory, that's a better predictor of academic success, future academic success, than it is intelligence and intelligence test. So the IQ is not as informative as working memory. So working memory is still related with learning. I don't know if by learning you can increase your working memory. And that's an interesting question. That's a very good question. Because what we find is that you have still working memory, has to do with the motor engine, if you will, the gray matter of your brain, mainly. The processing capacity, that's something you cannot do much about it, okay? But then you have this growth of the executive side of working memory that has to do with the deploying of strategies. For instance, mnemonic strategies. You can learn how to encode more information. For instance, I can give you a number of letters. If they make no sense, you will be able to store a few of them. But if you compose words that make sense for you, you can make use of your long-term memory. and then you can store far more information. So you can learn to boost your memory, to boost the performance of your memory. So I guess that answers the question. You can learn to store more information, and that will help you to learn better. So I would say it's kind of a virtuous circle. Both things are like feeding each other. That would be my opinion.
They reinforce each other, you're saying.
Sorry?
So you're saying that they sort of build and reinforce each other, repetitive.
Yeah, that is exactly what I mean, because, and that's very exciting. That's something I want to explore now, along with Michael Walker and another colleague, because there is this anthropologist, I don't know if I should mention this or I'm going far off the mark, but there is this Barry Boggin, I don't know if you're familiar with his work, that he says mammals used to have 3 developmental periods, so to speak. Is infant, I think, juvenile, and adult. But we humans have 5 developmental phases. We have infant, child, juvenile, adolescent, and adult. And I think this is very important because late childhood and adolescence is a period when you learn to deploy strategies. So this protracted development or maturation, I think, is key for us to boost our cognitive performance. I don't know if that makes sense to you.
Yes, it's helpful. It's a very complicated topic. It's hard to do research in this. So, every little bit of information is incremental and just adds to the overall, fund of knowledge picture.
Yes, and I have to be honest, I don't know much. I mean, it's something we want to explore because we believe there is something very exciting to discover there in this kind of elongated development of humans, how this can help you to make the most of this limited source of processing. I think that's exciting, but I don't know much. I mean, this is something I want to explore in the future.
All right.
Great. Thank you. Perfect. There's another question from Walter, actually, which is, what role does reward and punishment play in working memory development or interaction?
There, I don't know, to be honest. I don't know because, I mean, I see more reward and punishment, like kind of forming association between a stimuli and consequences, or a stimuli response. I wouldn't know how to link it to working memory. I don't know if you, Michael, have an idea. I myself don't know there is a clear connection, but it might be that I am not aware of it.
Well, I was thinking of just something very simple, like shocking an animal would, if you put a stimulus in front of them, you give them a shock, they avoid it. If you give them a stimulus and you give them a reward, they go for it. So in terms of working memory, how important is that versus repetitive actions? Certainly the amount of brain stroma, so to speak, between a chimp and a human is vast difference, as well as the neuronal connections, right? So as time goes on and that chimp or human are growing, right, they start making a working memory. It's just part of life, right? So I think of individuals as humans who are very stressed, like in war zones, or humans that are very rewarded, like those who have a good life. How much does conflict or difficulties create memories and personality so that they can go on as adults and survive lifetime?
I think there might be an answer to that, because working memory, you think of working memory as like having online access to information ready to use. So you can have new information you are using, or you can reactivate long-term information. but you take control of the situation. It's like when you use working memory, you are not going autopilot. So I guess when you talk of these associative processes, if you repeat something and has the same consequence, this is like gets ingrained in your brain and will trigger the response when the stimuli is there. But I believe this goes in another path, so to speak, because this does not involve taking control. And I guess this is more associative things may trigger responses that are more automatic. It's like when you learn to play an instrument or drive, at some point this becomes automatic. So it is not demanding in terms of working memory. So I guess it will be kind of different things, I think. I think Leonor wants to say something. She knows a lot about this. Maybe she can complement my views.
Hi, everyone. Yeah, can you hear me? Does it work?
Yes.
Oh,
Yeah.
okay. Okay. I just wanted to jump in because, yeah, so I agree with the associative components, and I just wanted to say that maybe, so there is the manipulative aspect of working memory, right? So the associative component that would be acting with the punishment and all reward and punishment is kind of, aside, but somehow it can, I would say, influence the motivation in the present problem solving. So let's say, the strength of association is sometimes stronger if you use electric shock or things like that compared to rewarding. So in the strength of the association that can then later be used as, a past information that's back into accessible state into working memory, this maybe could have an impact like this. So we've been wondering in some studies whether, increasing the strength of the association by using punishment instead of reward could, actually help later measuring some processes. So I would say maybe in this sense, but as Hector explained very well before, it's really the manipulation and the executive function control over the information that's important. And I would say that, the association between punishment or reward with a consequence is part of this information. So it's not the process of working memory itself, I would say. That would be my take on that.
Interesting.
Thank you very much. Just as the discussion was really kicking off, I'm sorry, but we do have to end. We do need to try and end on the hour because people have other things to get to. So I'd just like to say thank you again to our speaker, Professor Manrique, and everyone for their comments, questions, participation.
Yeah,
Really great
you.
talk. Thank you.
Thanks to you.
See,
Bye. Thank you.
see
Bye.
you next week.
Bye.
See you
Thank you
next
very
week.
much.